Entropy. Entropy is a fun topic. All right, so entropy is a measure of randomness. We sometimes think of it as a measure of disorder, but it's really what it comes down to is probabilities. And it's when we think about probabilities in terms of molecules and molecular arrangement, we can start thinking about a term called microstates. So a microstate is a particular arrangement of atoms, and an arrangement that has a high number of microstates tends to be the most probable. And so another way of saying that is that nature spontaneously proceeds towards the states that have the highest probability of existing. So this is where we're tying entropy in with the term of spontaneity. So if we look at this figure here, this is showing 5 different arrangements of 4 atoms in 2 glass bulbs that are connected. And in this figure, we can have atoms in the bulb on the left or the right, and we can think about how those can be arranged. If we take these 4 atoms and put all of them on the left-hand side of the bulb, they can be arranged in one way. Now we're just assuming each of these are labeled A, B, C, and D. Technically, within that bulb, there could be different spots for those atoms, but we're just going to say bulb left or bulb right, okay? So there's one way we can arrange the atoms with everything on the left, and there's another way we can arrange the atoms with everything on the right. So those microstates, there's one microstate in this arrangement. If we think about having 3 atoms on one side and 1 on the other, there's 4 different ways we can arrange these atoms. With A on the right, B, C, and D on the left, etc., swapping out one of the lettered atoms. And we can do that in terms of the left bulb or the right bulb, so having 3 on the right versus 3 on the left. Each of those have 4 different microstates or 4 arrangements. The one that is most probable, though, is having 2 atoms on the left and 2 on the right. And you can see all of the different arrangements of those. The number of microstates here is 6. And this makes this arrangement the highest probable. And so this is the arrangement that will occur spontaneously. And you know this because if you have a gas and you put it in a bulb similar to this and you connect another bulb and you open it and you let everything just come to equilibrium, you're going to have an equal distribution of atoms on the left and the right. And that's exactly what that's showing. Only now we're looking at it in terms of probabilities with a very improbable number of atoms. 4. It's very hard to do that. Okay, so entropy, we're thinking about probability, we're thinking about microstates. Okay. Questions on this? Okay. All right, so if we carry on this sort of idea and think about phase changes, I think I briefly mentioned this last time. Hopefully this is somewhat intuitive. Where we go from an arrangement in a solid, for instance, we have water in the form of ice, where it has a tight arrangement, atoms can be in a certain spot, they don't move around very much. We apply heat, or we allow ice at room temperature to turn into the liquid. The particles in the liquid can move around more, and so they have a higher entropy than that in the solid phase. There's more positions that the water in the liquid state can be in than in the solid state. And then when we go to a gaseous state, the entropy increases even further. We now have many more places where our water molecules can be, And so the entropy there is much greater than in the liquid phase. So in general, we have our entropy, which is S. I don't think I've written that yet. The entropy for the solid is less than that of the liquid, which is less than that of the gas. Okay, so that's the general trend that we see. So if we look at entropy and plot it versus temperature upon heating a substance, we would make a plot that looks something like this here. We'll have entropy S on our y-axis, temperature in Kelvin on the x-axis. You could put temperature in any unit, but this is in Kelvin, and I want to point that out. So at 0 Kelvin, this is a special point. This is going to come into our third law of thermodynamics. We have 0 entropy at 0 Kelvin. We'll talk about that in another couple slides. As we increase the temperature, so we'll be in the solid phase, the temperature increases and the entropy begins increasing. So we go from a place where there is no molecular vibrations or no atoms moving around at all to applying heat, and then atoms are able to vibrate a little bit in their positions. They're still a solid, but there's some slight movement there. Okay? Eventually, we get to a phase change, and this is where we see a sharp spike in entropy. So if we are heating ice, there's a point where you have, at the same temperature, where you have both solid and liquid present. And so converting from completely solid to completely liquid occurs in a major jump in entropy. This is referred to as the entropy of fusion. Every time there's a phase change, there's a big jump. And so you see going from liquid to gas, there's another big jump, and it's even bigger than that going from solid to liquid. And that's because the gas is moving much more quickly and has many more places where a gas could be compared to a liquid, more movement. Sorry. Usually that is off. I don't know how to turn it off now. Okay. Okay, and then again, within a phase, we see increases in entropy, but it's just gradual compared to that of the phase change, again, with the gas as well. Right. Questions on that? Yes?
So, I might be remembering this wrong, but there was like a question on the homework, and it's like, so if entropy like increases is not like exothermic, but endothermic.
Okay.
Is it like always like one way or the other?
It is not.
Okay.
I'll have to look at that question more specifically. Yeah, see what's going on there. We are going to, and we may get to it at the end of today, maybe not, but we are going to look at the relationship between entropy and enthalpy. That's what you said, right? You said enthalpy, is that right?
Yeah.
Okay. Okay, and so we've talked in the very first week or two about the entropy of solutions. And we saw for a formation of a solution that is exothermic, we don't really need to consider entropy, but if we have an endothermic solution formation process, we do need to consider entropy, because it's what allows for a solution to actually form. Now, I will say entropy always increases when a solution forms, so it's always there. But if you recall from chapter 13, the only time we need to use the definition of entropy and explaining why a solution forms is in the endothermic process. But no matter what, when we form a solution, we're basically making a mixture. So if we're going from a solid and putting it in solution to make it aqueous, that's going to be an increase in entropy. You take a take solid sodium chloride, you put that in water, it breaks apart into the sodium ion, the chloride ion. I'll get you in a minute. Those ions can move around more freely in solution than they did in the solid. Yes, Akash.
Is endothermic meaning favorable entropy from Gibbs free energy?
Say it again.
Is endothermic meaning favorable entropy due to Gibbs free energy?
Favorable entropy due to Gibbs free energy. Okay, plus T delta S delta G. Entropy, so favorable, yes. So basically, we make this equation, delta G equals delta H plus T delta S. Or is it minus? Minus. We're making it so that this equation is negative, and so entropy has to be large enough to account for a positive delta H. Yeah. Does that help? Okay, excellent. Yes, okay, so, we have a solution that contains a solute. We have another solution that contains another solute. We mix those together. Now the volume changes. Now there's even greater places where those different solute particles could be. That's also an increase in entropy. So anytime you see an increase in volume, for this delta G equals delta, we'll get to this, but basically for a reaction to occur spontaneously, delta G needs to be negative. And so if we have a delta H that is negative, the entropy must be large enough. Oh, if we have a delta H that's positive, excuse me, if we have a delta H that's positive, the entropy must be large enough that it makes the value of delta G negative. Yeah, but we'll talk about that. Next slide. An increase in the available volume, an increase in temperature, the number of particles that are moving around. All of those lead to an increase in the number of microstates, which is an increase in the entropy. Yes?
Can you repeat that again? You said entropy must be large enough to account for what?
Okay. So things that affect the number of microstates: temperature, available volume, number of moving particles, and then the number of reactants and products. So for example, we have two equations here. In our first one we have 2NO plus O2 forming 2NO2. So we have 3 moles of gas on the reactant side and 2 moles of gas on the product side. In our second equation, we have 2 moles of hydrogen peroxide, 2 moles of gas forming 2H2O plus O2. So that forms 3 moles. The side that has more gaseous particles has more entropy. So entropy increases as the number of gas molecules increases, or particles. So the side with the greater number of gas molecules has greater entropy. And so the other way of thinking about this is that only reaction 2 results in an increase in entropy. Okay. Make sense? Okay. So when we see an increase in entropy, delta S, the change in entropy going from products to reactants is positive. So again, delta S is going to be S for the products minus S for the reactants. So for which of these reactions would you expect delta S to be positive? Take a look at those. I think A, B, C, D. All right, yeah, so most people said B. So in A, we're going from 2 aqueous ions to a solid. That's going to be a decrease in entropy. Solid has less entropy than aqueous ions. In B, we have water in the solid phase going to water in the gas phase. That's going to result in a huge change in entropy. In C, we do have all gaseous products, okay? We have 4 moles of gas on the reactant side and 2 moles on the product side. And so that results in a decrease in entropy because we have fewer moles on the product side. And then with D, we're going from a liquid to a solid, so that decreases the entropy as well. Questions on those? So, we've been talking about microstates. You may have heard of Boltzmann. So, Boltzmann has, one of his famous equations was the relationship between entropy and microstates. It's given by S, entropy, equals K, which is the Boltzmann constant, times the natural log of W, which is the number of microstates. This equation is written on his gravestone in Vienna, Austria. So if you ever go there, you can check that out. And basically, you don't need to, we won't be applying this equation. It's hard to calculate a number of microstates. That's beyond the scope of this course. But basically, this relationship says that if you increase the number of microstates, you increase the entropy. Okay, so as briefly mentioned, the third law of thermodynamics, as we were looking at our phase change diagram. The third law says that a substance that is perfectly crystalline at 0 Kelvin has 0 entropy, or it has perfect order. There's no thermal motion, and there's only 1 microstate. Now, what the third law really gives us is the standard molar entropies, S naught, which is fun to say, fast. The standard enthalpies are given relative to 0 Kelvin. So when you see that, those S naught values written in your textbook, they're relative to the entropy at 0. Okay. Let's see. So we can notice a few trends when we're looking at molar entropies, and that is when you're looking at these entropies in a table, they're usually given at 298 Kelvin or 25 degrees Celsius, not at 0, because they're much more interesting and usable at 25 degrees Celsius. You'll also notice for a particular substance, just like we saw previously, that the entropy for gases is greater than that for liquids, is greater than that for solids. The other thing to note is that as the molar mass increases, the entropy increases. Why might that be? More disordered? Why? More what? More electrons? Yeah, there's just more stuff. More electrons, more protons, more neutrons, right? More interactions, yes. And we also see that the entropy increases with an increasing number of atoms in a particular substance. So for instance, like methane will have lower entropy than methanol, something like that. Okay? Yeah. So you're asking why is it not a 0? There must be something else that is usually given at 0 degrees. Oh, well, I think it's because this is relative to 0 Kelvin, and it's important to recognize that the entropy that's written in a table is relative to that at 0 Kelvin. So if we say 0 Kelvin, there's 0 entropy, and at 25 degrees, some made-up number essentially relative to 0 is our entropy for a particular substance. Let me see if I've written anything else about that. I don't think so. Okay. Anything else? So this, he asked, does that mean that a reaction at equilibrium has 0 Gibbs free energy? Yes, exactly.
But if it's not at equilibrium yet.
It is not at equilibrium yet. It depends on which way it's approaching equilibrium.
Alright.
And I'll show you a figure here. I think maybe the next slide or two. So how do we use those S naught values? We can use those to calculate entropy for a given reaction. So the change in S naught is equal to the sum of the moles of the entropy values times the products minus the sum of the moles of the entropy of the reactants. So very similar to what you've done with delta H. And if we see a positive value for delta S, that tells us we have an increase in entropy. If we have a negative value, it's a decrease in entropy. There are ways that we can predict, based on the reaction itself, whether a delta S value will be positive. And we sort of looked at this with our multiple choice question. But we can see a positive delta S when a molecule is broken into 2 or more smaller molecules. Or if we have a reaction that has more moles of gas on the product side than the reactant side. So there's more moles formed than we started with. And that's just for gas. Or, as we've seen, as a solid changes to a liquid, liquid to a gas, or a solid to a gas. So let's look at these 3 reactions. You can work with your neighbor and predict whether entropy will increase or decrease. questions? Let's look at this first example. Here we have 2 SO3 in the gas phase forming 2 SO2 in the gas phase plus O2 in the gas phase. Expected to see an increase or decrease in entropy? Increase, yeah. Why is that? More moles of gas. Whoop. Let's go down to the third one. P4 in the gas phase going to P4 in the solid phase. Decrease, yep. Okay, going from a gas which has lots of entropy to a solid that has very little, relatively. Okay, so I saved the second one because this one's challenging, right? So here we have ethanol, which is a liquid, plus oxygen in the gas phase, 3 of those, forming 2 CO2 in the gas phase and 3 water in the liquid phase. How many people think increase? How many people think decrease? Okay, yeah, so good, that's great. The correct answer is that you should see a decrease in entropy. And this is because the gas the difference in the entropy from the gas, which there are 3 moles of on the reactant side versus 2 on the product side, sort of dominates the entropy for this reaction. Even though we do have the breaking down of ethanol into different components, it's the number of gas that dominates, yes?
Is that a general rule for all reactions, that the gas would be more important to break down into molecules?
I would say in general, yes. But I think this is a good time or a good example to actually calculate this and just sort of prove it. And that was going to be my next suggestion, is that we look at the S naught values and calculate it. Unfortunately, I don't have those right now, but yeah, this is one that, in general, it's the gas that's going to matter the most. And that's simply because the entropy is so much greater in the gas phase. Okay, so I do have the the S naught values for the SO3 reaction. And so we can calculate delta S for the overall reaction using the values for each of the reactants and products. And we need to use the moles just like we've done with our delta H. So for SO2, we have 2 moles of SO2, and we have a S naught value of 248.1 joules per mole Kelvin. And so notice we have moles here. So moles are going to cancel, and we're going to be left with joules per Kelvin for your delta S. So watch those units. Okay, so we have our 2 moles times the entropy value for SO2 plus the 1 mole for O2 times 205.0 joules per mole Kelvin. All of that is summed minus what we have for the reactant, which is 2 times 256.7. And we'll end up with a delta S of 187.8 joules per Kelvin. So we expected to see an increase in entropy because we have more moles of gas formed, and that is a positive value of delta S. So confirmed. Okay. Questions on that? Okay, so now let's finally get to this Gibbs free energy equation that we've been talking about. So Gibbs free energy helps us predict whether a reaction is spontaneous. So now we're going to take our entropy knowledge, we're going to combine it with spontaneity and using Gibbs free energy to figure out if a reaction is going to occur without having to put in any energy. Okay, so this equation, delta G is our Gibbs free energy, equals delta H, the enthalpy, minus T, the temperature in Kelvin, and let's put that in Kelvin. And then times the entropy, which is going to be in joules per Kelvin. So enthalpy is going to be given in joules. So we're going to have Kelvin times joules per Kelvin and the T delta S. That's going to give us joules. And we're going to have joules minus joules. So delta G is going to be written in joules or kilojoules. I think mostly we see it in kilojoules. So if we know the enthalpy and we know the entropy for a given reaction at a certain temperature, we can predict whether a reaction is spontaneous. If delta G is negative, the reaction is spontaneous in the direction written. So it will spontaneously form products. If delta G is positive, the reaction is non-spontaneous as written. But the reverse reaction, Rxn for reaction, is spontaneous. Okay. What if delta G is 0? If delta G is 0, then the reaction is at equilibrium. And equilibrium comes back to haunt you. Okay. Delta G is negative, reaction spontaneous, it occurs as written. If delta G is positive, the reaction is non-spontaneous as written, but the reverse reaction would occur spontaneously. And if delta G is negative, or is equal to 0, the reaction is at equilibrium. So it's not going to go either direction. Questions on that? Or on anything? Yes?
This is really far back.
Okay.
But the trend thing where it says 25 Celsius and 0, and that
Okay. Okay, yep, it's coming up. All right. So in terms of calculating Gibbs free energy, we can calculate it in a number of ways. If our substances are in their standard states, then we can calculate delta G using delta H minus T delta S. So you'll know if substance, well, the standard state is this delta G naught business. So if you have values of enthalpy, delta H naught and delta S naught, then you have enough information to solve for Gibbs free energy this way. And so you can use tabulated values of delta H and entropy to calculate delta H naught and delta S naught, and then plug those into the equation to solve for delta G. You can also simply be given enthalpy and entropy for a given reaction and solve that. There is another way to calculate delta G. There are tabulated values of the Gibbs free energy for various substances, and just like we've done with delta H and now delta S, you can calculate delta G in the same way. Okay? I don't think we're going to do an example of that. I think you all are probably pretty comfortable with that type of calculation. Okay. One other thing to note here is, just like with delta H, elements in their stablest form is given a delta G of formation of 0. So this is for the diatomic elements like O2 and the elemental forms. So when you see a delta G of 0, that means it's either an element or the elemental form of that substance. You won't see that with the entropy though. So because those are all relative to 0, they all have some value for entropy. Okay, so why do we care about energy? Free energy can tell us how useful a reaction might be to do work. Only reactions that are spontaneous can be used to do work. And we can calculate the maximum possible useful work. You may have seen this before. The maximum work, W max, is equal to delta G. And that's at a constant temperature and pressure. And unfortunately, achieving maximum work is not actually possible, it's only hypothetical. And so we think about an example. You've got your cell phone, it's got a battery in the back, right? Ideally, all of the energy that's in that battery goes to power the phone, but you've probably experienced your phone getting warm when you use it, things like that. That energy that is being used to power your phone can also produce heat, and so you can lose energy in that way through heat or through the wires, through conduction in other ways. And so that's why this is sort of a hypothetical type of situation. So we never truly get W max out from a given reaction. Okay. So let's take a look now at what Braden was asking about, how Gibbs free energy changes during a reaction. Okay? So on our y-axis here, we're going to have Gibbs free energy. We're going to have the progress of the reaction on the x-axis, and we're going to have reactants on the left and products on the right. And you'll notice for this, the way this one has been written, right, the way this figure has been drawn, we start out with a high value of Gibbs energy. As the reaction proceeds, it decreases till it gets to a low point, and then there is some increase until we get to products. Okay. What do you think X is representing? The change, yeah. So this is delta G. Okay, X is delta G. Change between the Gibbs free energy of the products and the reactants. What do you think is represented at the bottom of this well? Equilibrium, exactly. And so this is when Gibbs free energy is 0, or delta G is 0, either way. And so when we have a reaction, we allow it to proceed. The Gibbs free energy, it occurs spontaneously. The Gibbs free energy decreases until we get to equilibrium. Okay? And if we wanted to form more products, we would have to put in more energy in some way. And so that's uphill, right? To completely go to products, we would have to put in energy. So that's what that is representing. Let's see. The other things to think about here, remember calculating Q for our equilibrium calculations? When we have equilibrium, our value of Q is equal to K, right? That's how we've defined that. And so that's at the bottom of the well here. When we have more reactants than necessary to reach equilibrium, Q is greater than K. So that's what's happening on this side of the figure before we've reached equilibrium, going from reactants to products. And on the right side of the equilibrium, we're going to have Q less than K, which means there are more products than would be achieved at equilibrium. All Does that make sense? We're gonna include some calculations with Q and K, so that's why I wanted to remind you of that right now. Questions? So let's look at a, this is for a spontaneous reaction. Let's look at the same plot but for a non-spontaneous reaction. Slide, see if I want to say anything here. I guess one thing to point out that's in this slide that maybe I didn't emphasize as much is that going downhill, no matter if you're starting from the reactant side or the product side, that's spontaneous. So even if we have a reaction where this is equilibrium and this is products, if we start out with products, we are going to go downhill a little bit. Okay, we may not get as much energy out as if we start with reactants and it has greater value of G. Okay, so that's just one thing. Keep in mind, going downhill, spontaneous. This slide. So for a non-spontaneous reaction, delta G is going to be positive. So we're going to start out at some value of the Gibbs energy, and we're going to end up with our products at a higher value of Gibbs energy. Okay? Where should we have our equilibrium lie? Towards the reactants or products? Towards the reactants. Okay? And so our figure is going to look something like this. Maybe a little more rounded there. There we go. Okay. Again, for this type of reaction, delta G is positive. Okay. If we start out with the reactants, we will be able to form products a little bit, but we're going to mostly still have reactants. We're going to get down to the bottom of this well, and we're going to achieve equilibrium. Okay? If we try to make more products, we have to put in lots of energy. Okay. So again, this is for a non-spontaneous reaction. Oh, it's already written at the bottom. And here we have, in a non-spontaneous reaction, reactants are favored. Okay, very good. Let me go back. Okay. All right, so we can relate our value of delta G to the equilibrium constant, and I mentioned Q and K, and this is why. So for our Gibbs free energy, delta G, and this is delta G with no not sign, delta G equals delta G naught plus R times T times the natural log of Q, where Q is equal to, just like what we saw in the equilibrium chapters. Okay. We can relate this to any value of our equilibrium, and we recall that at equilibrium, delta G equals 0. Free energy doesn't change. Also at equilibrium, Q is equal to K. All right. So this is delta G equals 0, and that's not delta G naught. All right, that's a different value. But if you say that delta G equals 0 and Q equals K, then I can rearrange this equation and write 0 equals delta G naught plus RT natural log of K, and rearrange that to do delta G naught equals R times T times the natural log of K. This value of K can be any of the K's that we've seen, KA, KSP, what else have we seen? KC, KB, all of those. It's an equilibrium constant. Is that a question? Yes, I forgot a negative sign. We usually put it on the right-hand side. Sorry, so delta G naught equals minus RT natural log of K. Thank you. What's that? Oh. Is it the Arrhenius equation? Ooh, I don't know, actually. I'm not sure how this one was derived. But R is our gas constant, 8.314 joules per mole Kelvin. And T is our temperature in Kelvin. All right. Next time. There are other questions on this? Yes?
What's the difference between delta G naught and regular?
So we'll go into that more next time. The delta, don't leave yet because we have to do a pumpkin thing. This is the best part. Delta G naught is at standard conditions. We'll talk about it.
Don't worry about it.
Don't worry about it. Yeah, so this is going to be loud. If you don't like loud noises, move towards the back or escape. Akash, yes. Well, I'm going to wear these because I'm standing right here. I was told that you can do this motion to your ears like this. That'll help, for sure. We're going to have to do that. Akash, since you have a helmet, would you like to be in charge of the fire extinguisher? In your bag? Yeah. You lay it on. I've got 2 fire extinguishers. Who's filming? All right, perfect. Okay. Oh, batteries. All right, so we've got this beautiful pumpkin. We are going to add to it, there's a container of water in here. We're going to add calcium carbide. When calcium carbide starts to dissolve in water, it produces acetylene. What's acetylene used for? Not quite bombs. It's a welding gas, so it's flammable. And so we are going to produce acetylene in this pumpkin, and then I'm going to light it. Okay? I've got all the gear. Those of you in front, definitely, or all of you, make cups, put them in your ears like that. All right. Not sure. No clue. If you don't feel comfortable sitting here, you really don't have to. I thought people should see this. All right, so I'm going to take 4 pieces of this. No, 5. It's bubbling.